Concrete is as much part of the urban landscape as trees are to a forest. It's so ubiquitous that we rarely give it any regard at all. But underneath that drab gray exterior is a hidden world of complexity. Hey, I'm Grady, and this is Practical Engineering. On today's episode, it's Concrete 101. This video is sponsored by Brilliant, more on that later. Concrete is one of the most versatile and widely used construction materials on Earth. It's strong, durable, low maintenance, fire resistant, simple to use, and can be made to fit any size or shape, from the unfathomably massive to the humble stepping stone. However, none of those advantages would matter without this. It's cheap. Compared to other materials, concrete is a bargain, and it's easy to see why if we look at what it's made of. Concrete has four primary ingredients: water, sand, also called fine aggregate, gravel, aka coarse aggregate, and cement. A recipe that is not quite a paragon of sophistication. One ingredient falls from the sky and the rest come essentially straight out of the ground. But from these humble beginnings are born essentially the basis of the entire world's infrastructure. Actually, of the four, cement is the only ingredient in concrete with any complexity at all. The most common type used in concrete is known as Portland cement. It's made by putting quarried materials, mainly limestone, into a kiln, then grinding them into a fine powder with a few extra herbs and spices. Cement is a key constituent in a whole host of construction materials, including grout, mortar, stucco, and of course, concrete. A lot of people don't know this, but every time you say cement when you are actually talking about concrete, a civil engineer's calculator runs out of batteries. I'm just kidding, of course, and you can hardly be blamed for not knowing the difference if you've never mixed up a batch of concrete before. Even if you have mixed some concrete, good chance it was in a ready mix bag where all the ingredients were already portioned together. But each ingredient in concrete has a specific role to play, and cement's role is to turn the concrete from a liquid to a solid. Portland cement cures not through drying or evaporation of the water, but through a chemical reaction called hydration. The water actually becomes a part of the cured concrete. This is why you shouldn't let concrete dry out while it's curing. Lack of water can prematurely stop the hydration process, preventing the concrete from reaching its full strength. In fact, as long as you avoid washing out the cement, concrete made with Portland cement can be placed and cured completely underwater. It will set and harden just as well, and maybe even better, as if it were placed in the dry. But you may be wondering, if water plus cement equals hard, what's the need for the aggregate? To answer that question, let's take a closer look by cutting the sample through with a diamond blade. Under a macro lens, it starts to become obvious how the individual constituents contribute to the concrete. Notice how the cement paste filled the gaps between the fine and coarse aggregate. It serves as a binder, holding the other ingredients together. You don't build structures from pure cement the same way you don't build furniture exclusively out of wood glue. Instead, we use cheaper filler materials, gravel and sand, to make up the bulk of the concrete's volume. This saves cost, but the aggregates also improve the structural properties of the concrete by increasing strength and reducing the amount of shrinkage as the concrete cures. The reason that civil engineers and concrete professionals need to be pedantic about the difference between cement and concrete is this. Even though the fundamental recipe for concrete is fairly simple with its four ingredients, there is a tremendous amount of complexity involved in selecting the exact quantities and characteristics of those ingredients. In fact, the process of developing a specific concrete formula is called mix design. And I love that terminology because it communicates just how much effort can go into developing a concrete formula that has the traits and characteristics needed for a specific application. One of the most obvious knobs that you can turn on a mix design is how much water is included. Obviously, the more water you add to your concrete, the easier it flows into the forms. This can make a big difference to the people who are placing it. But this added workability comes at a cost to the concrete's strength. To demonstrate this balancing act, I'm mixing up some ready-mix concrete with different amounts of water. For the first sample, I'm using just enough water to wet the mix. You can see it's extremely dry. A mix like this is certainly not going to flow into the forms very easily, but you can compact it into place. In fact, dry concrete mixes like this are used in roller compacted concrete, which is a common material in the construction of dams. For the next 3 samples, I use increasing amounts of water up to what is pretty much concrete soup. After the concrete has had a week to cure, I cut the samples out of the molds. It's time to see how strong they are. This is actually more or less how concrete is tested for compressive strength in construction projects. Obviously, I'm not running a testing lab here in my garage, but I think this will give us good enough results to illustrate how water content affects concrete strength. Plus, these cylinders look like they might attack at any time, and we need to deal with them. I made 3 cylinders of each mix, and I'll break each one, watching how much pressure the cylinder was applying at the moment of failure. And this experiment was too cool not to invite my neighbors over to help. We started with the samples that used the most water. It was no surprise that it took almost no pressure at all to break them, on average about 700 psi or 5 megapascals. You can see how crumbly the concrete is even after having a week to cure. All that water just diluted the cement paste too much. The next 2 samples used the range of water suggested on the pre-mixed concrete bag. These were much stronger, breaking at an average of 1600 and 2200 psi or 11 and 15 megapascals for the high and low end of the water content range. And you can really see the difference in how the concrete breaks. Finally, we broke the samples with the least water added to the mix. You can see how rough these samples were because there wasn't enough water for the concrete to flow smoothly into the molds. But despite looking the worst of the 4, these were the strongest samples of all, breaking at an average of around 3000 psi or 20 megapascals. On this shot, you can even see the crack propagating through the cylinder before it fails. It just goes to show how important mix design can be to the properties of concrete. Even varying the water content by a small amount can have a major impact on the strength, not to mention the workability and even the finished appearance of the concrete. It's impossible to say just how much I'm scratching the surface here. There is so much complexity to the topic of concrete, partly because it has so many applications, from skyscrapers to canoes and everything in between. In fact, no matter where you are, you're rarely more than a few feet from concrete, a fact that is inexplicably a source of great comfort to me. But I took less than 10 minutes to describe what is literally the foundation of our modern society. So I'm dedicating at least the next few videos to dive deeper into the topic of concrete. The next video will be about its greatest weakness. If you've got questions about concrete, put them down below in the comments and maybe I can get them incorporated into the next videos. Thank you for watching, and let me know what you think. If you're watching my videos, you probably share my passion for understanding how things work and wanting to apply that knowledge to your everyday life. To do that requires not only learning core concepts, but developing intuition. Brilliant is a problem-solving website that teaches you how to think like an engineer. Their courses are designed to help you gain a deep understanding of the topic. I love this one on solar energy that goes into lots of detail on the intricacies of these systems. To get started developing your own intuition, go to brilliant.org/practicalengineering, or just click the link in the description and sign up for free. The first 200 people will get 20% off the annual premium subscription. Again, thank you for watching, and let me know what you think.